In this question, we have ourselves a non-uniform linear charge distribution. And so what that means is that this rod that's extended across the positive x-axis is charged, but it's charged in a non-uniform manner. So for example, at the beginning of the rod, there might be a little bit of charge, but as we extend our way outward, the charge density actually increases. And how do we know that the charge density increases? Well, it's because they told us that the linear charge density, symbolized by lambda, is equal to b times x. So we can see that as we move away from the origin, in other words, as our x-coordinate gets bigger and bigger, then the linear charge density also gets bigger and bigger. They are proportional. So that's why we've sort of drawn extra charges as we travel further to the right along this rod. In part A of the question, we have to find out the electric potential at the origin. So, of course, the origin is right over here. We want to know, well, what is the electric potential over at that location? And each little segment of the rod is going to contribute to the electric potential at that point. So this little segment of the rod will contribute a little bit of potential at that point. Same with this segment, and of course, same with all of the segments that are extended along the rod. So what we're going to have to do is we're going to have to come up with an expression for the potential contributed by one of those segments. Once we have that expression for the potential contributed by one of those segments, then we can integrate across the rod. And what integration does is it adds all of the contributions to the electric potential from those little segments of the rod. So we're going to add basically an infinite number of little charged segments to get the overall electric potential contributed at the origin. So to get that process started, what we'll do is we'll choose that last segment that we drew. That last segment is located a distance x from the origin. Now that little charge segment right there has a very tiny amount of charge on it. It's such a tiny piece of the rod that the amount of charge on this little piece is pretty tiny. So we call that charge dq. And we're going to need an expression for dq. Let's talk about that for a moment. Now, what we're going to say is that just in general, charge is going to equal a linear charge density multiplied by a length. And in order for us to justify that statement, we can look at the dimensions of these quantities. So charge, of course, is measured in coulombs. Linear charge density is measured in coulombs per meter. And then the length that is under investigation is measured in meters. So the meters would cancel and we would have an equality. We would have coulombs equaling coulombs. So we sort of have justified the truthfulness of this little equation right here. Now, in the case of a tiny amount of charge, we would say dq equals the linear charge density is symbolized by lambda, and then the length would be the length of that tiny little segment. Now that little segment is so tiny that its length is going to be given also by differential notation. So just like we said that the charge is tiny and therefore we call it dq, because the length is tiny, we're going to call that length of the rod dx. So this is the equation that we can develop for dq. Now in the question, the linear charge density, which again was lambda, was given as bx. So we're going to have to make a little substitution here. We're going to rewrite lambda by substituting in bx. Now you might wonder, where are we going next? So we have this little expression for the amount of charge on that tiny little segment of the rod, but what about the electric potential? I mean, after all, that's what we're trying to calculate. So we might know that the electric potential given by a point charge is V is equal to K times the charge, and then divided by the distance from the charge to the location of interest. Now, here we're not really dealing with a point charge. We're dealing with a little differential element. It's kind of like a point charge. It's a very tiny amount of charge. So what we're going to say, actually, because it's tiny, is we're going to say dV. So dV is the electric potential contributed by that little dx charge element to the origin. So that little tiny charge element is contributing a tiny amount of electric potential, which we call dV. This is going to equal K times dq. You guessed it, it's a tiny amount of charge, so we use the dq notation. And then the distance from our tiny little charge element to the origin was symbolized by x. So we're going to fill in x right here. Now, fortunately, we developed a few moments ago the expression for dq. We're going to sub in that bx dx in for dq. And this is our expression for the electric potential contributed by that tiny little differential element at the origin. But we don't want the electric potential contributed by just one tiny little charge element. We want the electric potential contributed by all of them. Remember, there's essentially an infinite number of charged elements lined up across this little rod-like structure. And so to add an infinite number of electric potential contributions, we're going to have to integrate. That's what integration does. It adds an infinite number of items together, essentially. So when we integrate, we're going to integrate from the left end of the rod, which is x equals 0, to the right end of the rod, which was x is equal to 0.2. So we're going to come in here and we're going to add bounds of integration. Again, the lower bound is 0 and the upper bound is 0.2. Now you probably have already noticed that the x's can cancel here to simplify our integral. And of course, since we're integrating the right-hand side of this equation, we must also integrate the left-hand side. So integrating the left-hand side gives us v. That's exactly what we were looking for. And now we actually have to integrate this expression. Now kb is a constant, so we can actually factor out the kb to the outside of the integral, and that leaves us with the integral of dx, which of course is just x. And from our knowledge of calculus, we're going to plug in the upper bound, followed by the lower bound, but of course the lower bound is 0, so when we do kb times 0, we just get 0. When we subtract that outcome, it is negligible. So here we have kb times 0.2 meters. Let's plug in the values of k and b. Notice that when we plugged in the value of b, we made sure to convert it into a standard unit. It was given as nanocoulombs per meter squared. We changed the nanocoulombs to coulombs by just multiplying by 10 to the minus 9. So just make sure you make that conversion. And then when you plug this all into your calculator, you're going to get around 36. And this is volts because it's electric potential. And that is the correct answer to part A of the question. So that's the electric potential at the origin produced by this charged rod. But in part B, we want to figure out what's the electric potential at a different point. And that point is 0.15 meters on the y-axis. So let's draw a new picture to represent that. So here is our setup. We have marked another little differential element on the rod right there in pink, and we can label the distance from that differential element to the location of interest as r. So that's the distance between our differential element and the 0.15 meters on the y-axis. We have the distance from the origin to our little differential charge element, and that is labeled as x. Now, we're going to actually want to find an expression for r in terms of x. That way, when we integrate, we have one consistent variable. So we can use the Pythagorean theorem. We have a right triangle here. We could say that x squared plus the 0.15 meters squared is going to equal r squared. And then we just take the square root of both sides, and that way we have our expression for r in terms of x. Now with that in mind, much of our analysis will proceed similar to what we did earlier. So we'll kind of walk through that again. Remember, the potential of a point charge is kq over r, but then the potential expression for a little differential element is similar, except we'll say dv equals k times dq over r. And now we just fill in what we had for dq. Remember dq earlier? That was developed as lambda dx, so we'll fill that in. And then we will recall that lambda was equal to bx, so we'll fill that in as well. And then finally the r, the distance from our differential element to the location of interest, was up there at the top of the screen. It was the square root of x squared plus 0.15 squared. So that would be the electric potential contributed to the location of interest by that one single charge element. But to get all of them, we're going to integrate, just like before. We're going to integrate across the length of the rod from 0 to 0.2. This integral is going to be a little bit more interesting. Perhaps we can begin by taking the kb, which are constant values, and factoring them out. And now it's time to integrate. The left-hand side, of course, is easy. That's just going to become v. It's the right-hand side integral that's a little trickier. We're going to end up doing a u substitution. So what we'll do is we'll let u equal the expression underneath the radical. So that's going to equal x squared plus the 0.15 squared. And then you might remember from your calculus studies that you would differentiate both sides of this. So the derivative of x squared is 2x. The derivative of this constant is 0. And then this is actually du dx, so we can multiply the dx to the other side here. And then finally, let's multiply both sides by a half. And what this does is it shows us that 1/2 du is equal to x dx. So you can see that x dx right there. We're going to substitute that with 1/2 du. So let's come down here and do that. So we'll have 1/2 du, and then that's divided by the square root. And remember, x squared plus 0.15 squared was just u. So we'll put that u in there. We are integrating this, so we'll keep that integral sign. So continuing with our u sub, we'll factor out the 1/2. We'll rewrite the 1 over radical u as u to the -1/2. And then we'll just use a basic power rule. We'll add 1 to the power to make u to the 1/2. And then we'll multiply by the reciprocal. The reciprocal of 1/2 is 2. We still have that factor of 1/2 that we had taken out. Oh, look at that. 1/2 times 2 is just 1, so we can kind of cancel those out. And so we're left with just radical u. But our u was the x squared plus the 0.15 squared. So that completes that integral. But let's not forget we had factored out a kb as well. So we'll have a kb parked in front of our answer. Plus we have the bounds from 0 to 0.2. So let's tidy this up a little. And there we have it. Now we're going to take the 0.2 and plug that in first for x. And then we're going to plug in the lower bound afterwards and then subtract the outcomes. So here's what it looks like. And then we'll plug in the values of k and b. Again, we converted b into coulombs by multiplying the nano by 10 to the -9. We end up plugging this in and getting approximately 18 volts. That is the electric potential at the location 0.15 meters on the y-axis.